Draft science video. So I thought I would talk about inertia and the basics, the fundamental mechanisms, and just do that. Because yeah, I know some of this is all very complex. It's very simple, but it's complicated to, until you know it, you don't know it. It's like anything. You learn how to ride a bicycle. Bicycle riding is really easy. But it's not so easy when you're first trying, because you have to do certain things mechanically that don't seem right. And you have to get used to that not seeming right part for a second, and then all of a sudden you say, oh yeah, it's perfectly right. Right, first I have to balance before I can go, yes, or I have to be going to stay balanced, or those kind of rules. So you have to learn a couple of little rules, and then it's, oh, this is easy. So anyway, so first I'll start with this Ken guy. I mean, there's two places in here where he does this. They debate somebody or anybody. At one point it's anybody. At this point it's not anybody. I guess he wants to debate PhD people, but whatever. If you're afraid of their seconds, I mean, I'll second for the PhD people. I'll defend their bullshit, and some of it is bullshit, but I'll defend it because it's bullshit heading in the right direction, whereas your bullshit is heading in the wrong direction. The non-material universe is, yeah, that's crazy. Anyway, so.
Yeah. Let me tell you what. You go find that schmuck, okay? And then offer them $1,000 or $10,000 reward. I'll pay it out, okay? I'll pay him $10,000. Let's have a debate on.
Well, look, maybe I'll pay you some money to show up to the debate. How about that? Or maybe we'll just have a prize or something, and let the audience decide who gets the money.
Live stream. We'll record it. You bring any of those people that you want, and we'll have a debate.
Yeah, so he said Skype before. I think Skype would be the place to do it.
On the nature of a field, and we'll have a debate on virtual photons, and I know all of their back doors. I know all of their weaknesses. I know all of their Achilles heels.
Yeah, well, I don't know all yours, but I'm going to trip over them so easy and obviously. I mean, you're laughing at other people, right? He's just mocking because he's saying, waves in what? Because somebody says there's a wave. And you're saying, well, what are you saying? Perturbations in what? A non-material, non-entity. I mean, well, that's sort of, I mean, you can't get more catch-22 than the code or the rule is written in invisible ink in Martian, before the universe existed, so there was no words. I mean, there's just no way to read it, right? Because you're just not going to make it possible to make that coherent. And then you talk about how nature's not a crack whore. Frankly, writing an invisible perturbation sounds like fucking goddamn crack horror-y. But anyway, I just like to get to the basic mechanical things. Words like inertia and what they're supposed to mean. How you can practically say something like a lack of inertia and make sense. So I don't think you can. But anyway. So on to business. But I'm just saying, I can't, what can I say? I mean, yes, you say you debate. You say you win your debates. You say you're the king of kings, and yet you can't man up when I ask you to. At all. Even close. I mean, really. What are you afraid of? It's going to be public. I mean, it's not like I can do anything sneaky. Can't give your camera a virus or anything. Well, anyway, enough of that. Alright, so we have this idea of inertia. I throw a baseball and it just keeps going. Let's say I throw it in space and it just goes and goes and goes and goes and goes. Now, physics doesn't give us any explanation for this go-y thing. It just says it has momentum. It's going. It's in the going way. But if I took a baseball that's not going and a baseball that's going, or I just pulled them out of the universe, they're not going to be able to tell the difference between the going baseball and the not going baseball. They're going to say it's the same baseball. The going is some sort of, it just goes. Obviously that's not a very good explanation in my opinion. So I could say, like, okay, well, we know that if we take the baseball and we take it apart, we know all the little pieces are going. So it's like the Earth crashing into the sun kind of thing. We know that if I broke the Earth into 1,000,000 little apple-sized pieces, all of those pieces have velocity all of those pieces have acceleration towards the sun, and all of those pieces will just keep doing what the Earth was doing. So somehow the inertia, the velocity, is inside of the pieces. So let's go deeper. Let's go to the atom. Well, we know the atom is made up of some moving pieces. So isn't that a little bit of a giveaway? Well, how do they move? I mean, how do they know to go that way and that way and that way? How do they know they have velocity? And how do they know they're being accelerated? Yeah, well, they really can't, can they? So something must be doing it to them. Get it? They must be in some sort of condition. And the overall matter must be, the whole atom somehow has to move. You can't leave pieces of the atom behind. And there's no explanation of any energy profile where you can say, well, if I pull on an elephant, there's a dead elephant, and I pull on his trunk to try to move him. Well, it's not going to be too damn easy, because I'm not pulling just the trunk, am I? I'm pulling all those connected bits. So we know we can't just say, well, atoms move because one piece of the atom is going the right way and it just drags the rest of the atom along. Well, it can't really do that because it would need like energy to do that. It would need superpowers to be able to do that. So I would argue that we have to come up with an explanation that's even smaller, more granular. And that's where physics has failed. Because they came up with the word quanta, they come up with these ideas of preposterously small things, you know, forces that are 10 to the minus 27th. They do that. You know, they say they can measure shit that weak, and yet they can't figure out that maybe shit like that is what's telling all the little stuff which way it's going. Maybe that's where the identity is, and that velocity is something something has. It really does have it. It possesses it. So when you gain velocity, it's not something happening to you. It's something you're doing, something you possess. If I do compare a baseball moving to a baseball not moving, their configuration of their bits is going to be different. Now, it's not a difference that's easy to see, but it's there. So anyway, so I'll give you the better version of reality. One way you don't have to have virtual photons and all this other crap, because you can have real ones. Alright, so I've tried to think of different ways to make this understood, so I'm just going to try it this way, and it'll either work or it won't. Yeah, I know that sounds kind of, hey Derry, you can't just do it that way. Well, I'm going to try to do it just that way. Alright, so say we have a bit of something. We're going to start off with like a proton. So we have protons and electrons. And we know those two things are kind of functioning oppositely. Okay, that's why they attract and whatever. It's because whatever they're doing the opposite of each other. Then I'll try to explain what they're doing and then you'll get what I'm talking about. Okay. Alright, so inside of this proton, we know there's lots of energy in these proton, neutron, electron. We know there's lots of little bits inside of them because when we break them all to pieces, lots of little bits fly out, lots of little photons in all kinds of frequencies, and they can cause all kinds of trouble. So we know it exists. This stuff is inside of this stuff. And so I'm arguing that it's all about this polarization thing. So when you say you have something, what I'm saying the something is, it's sort of like this. Okay? It's full of force because it's three-dimensional. So let's understand that first off. That matter, what makes matter is the three-dimensionality. Maybe there's two-dimensional matter. I'm not going to argue that yet. But it's at least more than one dimension, which means it has substance in these dimensions. Like light would only have substance in the one dimension it's traveling in. It only has mass where it can land. It doesn't have mass in any other dimension but the dimension it's moving in. Can't affect anything in any other dimension. It's the nature of it. It can't go two ways. It can only go one way, and therefore it can only have mass in one direction. Where we're made up of forces going all kinds of ways, and that's we're radiating our mass in all directions. That's pretty intuitive and sensible, I think. Alright, so you have inside of you, at any one moment, what I would do with this image is I would say to you that the only bits that are your mass, so you have all kinds of quanta inside of you at any 1 second. If I froze you any 1 second, there's all kinds of bits. So say this little blue blob's moving that way, and this one's going that way, and that one's going that way, and they're all different polarizations. But the only thing that really defines the proton, let's say, are these 5. And if the proton is stationary, okay, if it's not moving, there would be an equal number of arrows going that way, as up, as down, as in, as out. So there would be balance, an equilibrium, and that's why it's stationary. So these are all of this particular polarization. So let's just use red polarization and black polarization for this argument. So the proton, red polarization defines the proton, and for the electron it's going to be black polarization defines the electron. And so what's happening in these interactions is, as I've tried to explain before, pure kinetic interactions create a kind of obvious problem. I mean an obvious perceptual problem, in that you have two things coming in. Okay, this is the more obvious scenario. So you obviously have two things can crash into each other. Now the one scenario you can't have is one thing crashes into the back of another thing. Okay, so because they're all moving the speed of light. So yes, you can't hit a photon in the back end. You can't have a rear end collision. You can only head on and perpendicular. Those are your choices. And obviously in this perpendicular thing, there's this idea of, well, what happens? Does this reflect off of this, and this reflect off of that? Or does this just go through this, and this just go through that? There's a way of interpreting it. And the argument I'm going to make is that there's this thing that happens with matter. So matter is defined by red and black polarization, and the rest of the polarizations matter doesn't interact with. It doesn't care. They're of no significance to material function. The only polarization that matters to matter, that only makes matter, is the black and the red. And so in this scenario, what you have really is you have a direction and a polarization. So if I change this to black and say this is black polarization, you could come up with a scenario where, where black doesn't go through, the polarization doesn't go through, and it exchanges. And so the black polarization goes this way, and the red polarization goes that way. It always reflects instead of goes through. And the same scenario for this thing. So we could have a black head-on collision with a red, and what will end up happening is the black goes this way, and the red goes forward. So instead of bouncing. No, I mean they do reflect, I'm sorry. They reflect instead of going through each other. Alright, so what I'm arguing is that when a bit of energy now comes into a proton, and let's say it's a black, what's going to happen is, and let's say it's going to hit this one because it's going down. So the black will go through, it'll hit this thing, and this will now have a new direction. So the direction will stay in here. The polarization stays, which means it's red. So it took the direction of the black, but it retains the red polarization. And what it's going to get rid of is black going this way. So the black goes in, it comes out this way. So, and the red stays because the red is the matter. But what has changed is its direction. So in a sense, this piece of matter now doesn't have equilibrium. This proton now, see if there's no black equal black on this side, in the next moment, if a black doesn't come this way and reverse what just took place, this thing is going to keep the imbalance. And the imbalance means it has, let's say, 15 little arrows going that way, and it has 14 going that way, which means over time it's going to move. It's going to have velocity. So this exchange, a black goes in and a black comes out perpendicular, that happening, that event, represents acceleration. So this is the perpendicular EMF, the electromagnetic force, that is emitted by this accelerating particle. So this is a proton. When you accelerate, you produce black EMF because it converts black, okay, into it changes the direction of its red polarization and emits the black in the perpendicular. So it emits the black direction in the perpendicular with the black polarization, and it obviously retains its red polarization because that defines its material form. Now, what could be also happening as this is happening, you could just have a regular red, okay, of the correct polarization, that comes down, and this regular red interacts with this black, and the same thing happens. A black will leave, and this, now we have a new red with arrow, and what will happen is one of these then will just escape the matter. It's no longer going to be part of the matter. So the matter will always be made of the same number of polarized bits. So when it gains a new piece of matter, it lets go of an old piece of matter. It's just keeping these polarizations. So it can interact with field polarization, in that it's just that the identity of what we define as the matter will just change, and that probably happens with acceleration also. I mean, that's partly how you could accelerate something, is to create a new bit forward and let go of a bit in the end, and then create a new bit forward and let go of a bit in the end, and that'll work the same way. But I really didn't want to confuse this by explaining that there's probably more than one way for this to take place. If we just think of those polarized positions as being static, that the polarization is always there, that it's in a form, a geometry, and I'll try to explain that geometry, but I would say that inside of protons and electrons is a mechanism. Just like we could understand there's a mechanism that holds the atoms together, like the electrons are spaced in the proton. Inside the proton there's the same kind of balance between quanta, okay, that creates a rigid form, and it's that rigid form that moves. That gets its arrows changed. So it has more arrows going one way than going the opposite way, and then it'll go that way. And it's really that simple. It's just arrows in, arrows out. So then you can sort of understand, I think this is understandable. So what you're okay. So what you're seeing here is this idea that black creates acceleration. So when black comes in, it's going to change. If any of these are changeable, you know, if they were all going, if all these reds in here were already pointing that way, this black wouldn't have anything to hit, would it? Right? Because I can't hit the back end. So I can only hit something going the opposite way, or something going up or down or in and out. And those are the only ones I can hit. So obviously if it's already moving very fast, I can't hit it. But we know that there's, as long as there's bits in here that it's not completely going the speed of light in one direction, which that would require, we know these other bits exist and that it will impact them and it will create acceleration. So this is what happens when the particle gets accelerated. And this is particle, again, let's understand, the particle is not a particle. The particle is a collection. It's a school of the bits. The bits are doing all the action, all the work. The field bits, whatever you want to call them. The photons. The virtual photons, no, they're real photons, and they're the force carrier. Their velocity, their orientation is absorbed, both in terms of their direction they're traveling is absorbed, and then their polarization is released, or vice versa. Okay, so and so you can sort of understand that this emitted force is always going to, so it's always interacting with black, it's always emitting black, and it's keeping the red. So you can sort of understand that emitting black means that I'm going to be hostile to other protons, right? Because I'm producing the very thing that makes them go in the direction of the force. So I'm going to be emitting, eventually, black in all kinds of these directions, okay, as the consequence. Black is going to be now taken from coming, it could come in one direction and it's going to be leaving in all the directions based on these geometric interactions. And so I become hostile to any other proton. There's no way I could push two protons into each other, because the two protons are going to keep getting their arrows changed in a direction saying, get away, get away, get away, get away. All the arrows are going to change in the opposite direction that the force is coming in. I mean, in the direction the force is coming in. And they're going to be expelling it in this perpendicular way, which means now they're going to repel anything near them. So it feeds on itself in a sense. And so the argument is that the electrons are doing exactly the opposite. So they're red sensitive and they're black, okay, in terms of the polarization that defines them. So they're defined only by black polarization, and it's when a red comes in that their black polarization absorbs that direction and emits the red polarization perpendicularly. And so you can sort of understand that if I shoot red, okay, at a proton from an electron, it doesn't care. It only cares about black, and the electron only cares, so if a red one comes in here, it's not going to affect this matter. It can't affect reds. It can only affect blacks. And there's no blacks in here. So the red's just going to go right through. And vice versa for the electron. The black is coming at it. It doesn't care about blacks, so that doesn't mean anything to it. So you can kind of see if there's any external, if there's any external blacks coming in from the outside on the proton and any external reds coming from this side on the electron, the two will get pushed into each other. So you can sort of see that mechanism. Now with gravity, the two forces, this is the only thing happening. This gravity starts here. Gravity starts with this effect on protons and electrons, and in a kind of a sideways way, in the sense that a regular orbiting body is got full of electrons and protons, and when it accelerates, it means the electrons and the protons both absorbed black and red, right? They absorbed black and red coming in this way if I'm moving towards a body over here. They absorbed black and red coming in this way, and they emitted black and red going up and down. And there's no black and red going this way. There's only green, green, black, purple, I mean not black. All the other colors go through it. Okay, but it's not going to be able to sustain. It's going to be emitting a reduced number, substantially reduced number, of black and red. And the other body is going to also be doing the same thing because it's accelerating towards it. So it's absorbing all the black and red arrows going this way. So we have lots of black and red arrows coming from the outside world, very few black and red arrows in between us, and the only thing that are gravitationally significant, the only thing that can make electrons and protons move, are black and red arrows. So the absence of black and red arrows in here means there's going to be a low pressure, and I'm going to move towards the other thing, and the other thing is going to move towards me. There's a lack of black and red arrows to push us away from each other. And so that's the nature of gravity. So gravity is essentially only capitalizing on a kind of 2% of all the gravity pressure available. There's only two kinds of polarization, this and maybe this, and all the others are being ignored by the material form. So the material doesn't care about all these other polarizations. It only cares about the kind that it's polarized sensitive to. And that's it. Now what exactly that polarization is going to depend on how the geometry of 3 dimensions. They're coming from different directions. So obviously it's not there's no standard in 3 dimensions for a this and a this. That's a one-dimensional shape in a way. Well, 2-dimensional. And 2-dimensional distinction, and there's 3 dimensions. So it gets a little more complicated. So polarization is more of an expression of an exact geometric vector, but I don't want to get really complicated. Because I think this is good enough to explain, to make it understood that whatever you call polarization, it's a feature of the thing. It's a characteristic the little quantas have, like their velocity, like like the direction they're traveling in. Their polarization, their shape as they're flying, is a fact. They're either flying vertical to their, they're either doing this perpendicular shape to their velocity, or they're doing some other angle to their velocity. Alright, and that would be the difference. Alright, but anyway, so you can just sort of see that the absence of black and red would be it's all coming out perpendicular. It can't affect the things as they're moving together. Now, intuitively, there's a little bit of evidence for this truth, in the sense that you can sort of see it with things that gain velocity, that they sort of seem to create these invisible layers, along their surface, where everything seems to get pushed out. And you can see that in a wave tunnel or something, a wind tunnel. You can sort of see that effect taking place. And obviously in a wind tunnel it's not the same thing, because the wind is what has the velocity, which makes it a little more complicated. I mean, the matter of the atmosphere is the one doing the moving, not the object. And that is kind of an interesting fact, that why wind tunnels aren't perfect representations of the real dynamic, because in the real world your actual velocity has something to do with what is producing the perpendicular force. But it's always going to be perpendicular, so in a sense it doesn't matter whether the air molecules produce the perpendicular force or the plane wing produces the perpendicular force. The force is going to be produced either way. But anyway, I won't get into that, because that would require a whole bunch of extra physics to learn to be able to be totally competent in what I'm saying. I'm just saying it does seem intuitive that you always kind of see that effect where the force is always pushed away from the object moving with velocity, and the faster you move it, the more it gets pushed away. Not terribly, not exactly an argument against what I'm saying, right? Might not be an argument for it, but it's definitely not an argument against it. It looks like it supports what I'm stating, but I don't have the competence to say that's for sure yet. Alright, sorry, it's hot in here. Alright, so that's all I really wanted to do, was just clarify this one thing. I mean, somebody left some jerky comment I should make a 10-minute video, and that some kind of other bullshit. It's like, look, I'm not, number one, I'm not making these videos as my, I'm sorry, but I'm really not making these videos to make arguments to people who know nothing about physics. I mean, you really can't do that. It's just, you have to give physicists some credit. They're not complete imbeciles. I mean, if it was so obvious and so simple, then I wouldn't have to do this. There is some convolutedness to this, and you do have to understand fundamental principles to be able to make these arguments. And I really don't have the expectation that these videos are going to work on Joe Smo, for example. I'm trying to use regular human language, and I'm trying to point out what the arguments are about, and I'm trying to make them understandable, but I don't have the expectation. My expectation is to have an argument with somebody who knows physics, who can debunk what I'm saying, who can actually say that can't be the way it is. That's what I'm looking for. That's the test. See, I'm testing these theories. I'm not promoting them at the moment. I'm just looking for a good test. And I'm not getting that, of course, because they're very good theories. Yeah, people can't debunk them easily without insulting me. So, obviously, I'm winning. Obviously. And other people are cowards. I ask them to show up for the argument. They won't show up for the argument because I think they know they're in trouble. Because I got the argument. I got the truth. Anyway. So is there anything else I wanted to make clear on this? So anyway, I was just trying to point out that this is where it all starts. Gravity really starts with the little bits, right? It's a nuclear force. It's not moving planets. It's moving protons and electrons. That's what it's moving. And ironically, or holy shit, that's weird. But yeah, that's the real truth of it. And when you have inertia, when you have velocity, what's really happening is you're gaining quanta moving in a direction. You are possessing your velocity. It's not an accident. You actually have bits in your polarization holes, right? So every millisecond, every zillionth of a zillionth times a zillion squared of a second, every second times 10 to the minus 500th, okay, a tiny, tiny, tiny amount of time, these things are exchanging, these arrows are changing. So this is happening on a scale that I can't describe to you how many times this changes in a second, but it's a lot of times, lots and lots and lots of times. And it's averaged over a whole period of time where its direction is. But it's going this way, and then it's going that way, and then it's going this way, and it's going that way, and the field over time is, you can sort of understand that it's really just going to be about how many black arrows came in from this side and how many black arrows came in from that side, and that's all that's going to decide where the hell this thing, okay, what configuration it's going to have over time. And if it's gotten 5 more black arrows, it knows it has 5 more black arrows. I mean, it's going to, the effect of that is going to be translated into a velocity, and when each arrow hits, it gains acceleration, so it has 5 acceleration arrows ahead. That acceleration was real, it has the velocity, and until 5 arrows come in from this way, it's going to keep it. It's going to have it forever until something takes it away. Until something puts black arrows going this way to change and get back to equilibrium. So it's just breaking equilibrium. It's not a lack of inertia that makes the universe go round. It's a lack of equilibrium in these polarized locations, in these locations defined as me. If I have more me bits going that way than that way, I'm going that way. And the more imbalanced that is, the faster I'll go that way. Now, I always have to go much slower than the speed of light, just because the imbalance has to drag along all the other bits, which means it has to spread into all of my polarized cells, and each one of those polarized cells has to go this way for some period of time. So all of them have to carry the arrows going that way for me to go that way. It migrates to all the locations, is all I'm saying. Whatever amount of imbalance you have, one extra that way, well, the one extra has to be multiplied or divided into all of the locations to find out how fast you're going to move relative to the speed of light. So you just divide by that, whatever that huge number is, one extra arrow over the total number of polarized locations, which could be a zillion, right, times the speed of light, and that'll tell you how fast you're going. All right. So anyway, I don't want to go any. I just want to do this simple thing, keep it simple, just so you understand. This is the nature of gravity. So gravity, the nature of gravity is in the nature of the polarizing effects of electrons and protons, and that protons and neutrons are the only bits moving in a material substance. I'm sure I won't get into neutrons, because neutrons are in a special class, but I'm sure they're doing something. Okay, they're not being left behind, so clearly they have their own mixed polarization. Maybe it is just that, it's mixed. They're not really neutral, they're just mixed. In the sense that they have both plus and minus, both red and black polarization that define their structure. So it's a net 0, because for every black that's in them, they have a red. So they can't repulse or attract, because every time they shoot a black arrow, they end up shooting a red arrow and do exactly the opposite thing. They undo the blackness by putting the redness back in, so to speak. Something like that. Yeah, I don't want to get into that mechanics, but that's probably what it is. Probably. Yes, it needs to be explained, but I'm not doing that now. Someday. And I'm just saying, don't get lost worrying about neutrons. Because they're like Frankensteins. And so let's not even get into the anatomy of Frankenstein. Let's just deal with the things that we know, which is we have a negative and we have a positively charged nuclear bit, and we can understand what is the nature of that charge, which is one thing is expelling something it can't stand. Okay, they're both expelling smelly sweat that they can't stand the smell of, but it's quite benign, entirely benign to these other things that are expelling their own force they can't stand. You know what I mean? That's the push together. Anyway, I think I don't want to put. No point in going any further. I think that's understandable. Protons and electrons are configured of opposite polarization. The opposite polarization creates an opposite filter, and that's why they attract and they repel, because they're doing the magnetic thing essentially. And in magnets, the argument's going to be is that they're not only, like, they don't just do the black arrow comes in, black arrow goes out. Any color arrow comes in, black arrow goes out. They convert everything to black polarization. And conversely, on the red side of the matter, red polarization. And that's what makes magnets so powerful. So anyway, enough. I think I made the argument. Counter arguments, please. I'll probably have a live room the next day or two. If you want to do Skype, then PM me, and we'll see about doing Skype if that's the only way you can imagine making your arguments. But yeah, they have to be arguments that have physics in them. Can't make arguments about how big my anus is. Really not relevant. Fuckers.